Yeah, for Liz, right? They probably won't be able to hear you like they can hear me. All right, so here's what I want you guys to think about. This is the last really new thing that we're adding. We've been talking about, my pen's not working, heat of reaction. That's what we found for the candle. That's what we found for the marshmallow. And in both of those cases, we had to do it experimentally. So if you think about, why won't that, there we go. You know, we had the one experiment, here's our candle, we used it to heat water. We found delta H for the reaction, for the combustion of our paraffin wax, C25H52, and we found that number. We, saw how much energy went into the water, assumed it was lost by the candle, did it per gram. Great. So we found something in units of kilojoules per gram. Then in the lab, you guys did really the same thing, except you had a marshmallow, lit it on fire. We made some more assumptions about where the heat was going, but you found delta H of reaction for the combustion of a marshmallow, which was, mostly sugar inside of a marshmallow. And again, you found that in joules or kilojoules per gram. The thing is that both of those, in order to find the delta H of reaction, you needed to do an experiment. And now, that's not practical all the time. But I want you to think about what kind of a question might pertain to that. So let's consider the candle for a moment. I'm not going to solve this question, but I want you to understand kind of where this heat of reaction is useful. So if I have a question like, if, let's say, 2.95 grams of candle and delta H for reaction, all right, anyone still have their lab handy? What was the delta H reaction for the, or anyone have it in their notes? What was the delta H reaction for the candle? Was it negative 5,500 or negative 7,900? Negative 7,900. So we got negative 7,900 kilojoules? Joules. Was it joules? Okay, I can't remember. I don't have it in front of me. Joules per gram. That's what we got. So if 2.95 grams of candle is burned and used to heat 100 grams of water that was originally 22 degrees Celsius, what will the final temperature of the water be? So in a problem like this, and this is a type of problem, and you'll encounter some of these kinds on the worksheet, but when we find this delta H of reaction, it's used for stuff. Like, it helps us to know how much energy we get out of the candle. So if I have that information, my screen is not cooperating. Can't write. Oh, now it's black. Okay, and highlighter. Awesome. If I have that information, what can I find for the candle based on that? What am I going to be able to figure out for the candle? Mike? How much energy? What? Yeah, so if I know that I have 2.95 grams of candle, can I figure out that's how much is burned, right? That's how much we lose. Does that make sense? So there may have been more candle, but I literally used up 2.95 grams of my candle. So if I have 2.95 grams of candle that's burned, and I get negative 7,900 joules for every gram of candle burned, I should be able to find the amount of joules from the candle. Does that follow? And then if I have water, I have a mass of water, I've got a mass of water is 100 grams. I've got a temperature initial is 22 degrees Celsius. Of course, I've got a specific heat of water. I don't know the final temperature because I'm trying to figure that out. But what equation am I going to use for the water? The SM delta T. So I'm going to use Q is equal to SM delta T. I know the specific heat of water. I know the mass of the water. Do I know the Q? Sure, because I know I get some negative number here. But I know negative Q lost equals Q gained. And so that helps me find Q. And from that, then I can find, this is T final minus T initial, I can find T final. So we can use that heat of reaction to figure out how much energy is lost by something or gained by something, and maybe use to heat or cool something else. The thing is that in the lab, that's how we got this. And today what I want to talk about is we need a way to get that on paper. We can't have to go back in the lab every time we need a heat of reaction. We need another way to get it. And so that's what today is going to be about, is trying to find another way to get that. So, we're going to talk about something known as Hess's Law. And Hess's Law says this: whether a reaction occurs in one or many steps, delta H for the reaction will be the same. I'll show you what that means graphically. All right, we looked at this equation before, burning methane. Like those big methane bubbles that we did in the other room. All right, let's balance it. Okay, it's balanced. And we also did this graph already. So this was energy, like this is the course of the reaction. We said, here's my reactants. We had a little activation energy, and here are my products because it was exothermic. So we ended up with less energy than we started with. Hess's Law says, great, the difference between here and here, that's delta H. And that's what it would look like if it happened in one step. But let's say, maybe, what if instead that reaction, here's my reactants, I know I moved the graph down here a little bit, but it has the same amount of energy, we're starting here. But what if it happened in many steps? What if maybe one thing happened and we ended up here? And then maybe another thing happened and we got some different products. And then finally, it turned into reactants, CO2 and water. Well, what Hess's Law says is it doesn't matter how you get there, still the difference between products and reactants is going to be the same exact delta H. So it really says, we don't care if it happens like the molecules slam together, bam, in one step you have products. Or if maybe they slam together and they form something new, and then those hit something else and they form something new, and then those hit something else and they form something new, and finally they form the products. It doesn't matter how you get there. The difference between the beginning and the end is still always the same number. All right, so I'm going to show you how that actually plays a role for us. So I'm going to teach you what I like to call Hess's Law long, sort of the long method. It depends what you're given, which method you would use. But in this method, what you do, and I'm going to show you an example, is you actually manipulate possible steps in the reaction and their delta H's so that they add up to the desired reaction. and give you the delta H for the reaction. Now there's a lot of this that isn't necessarily going to be listed in your book quite like this. This part a little bit. All right, so what I'm going to do is I'm going to show you an example. So Hess's Law is all about if we take a look at given steps in a reaction and their energies. And I need to actually find my, oh, there's my energies that I need. So here are some possible steps, and I'll show you how to do this. So here are some possible steps, and we're still looking at this reaction. CH4 plus 2 oxygen yields carbon dioxide and 2 water. This is still the reaction we're interested in. I'm going to give you some possible steps. These would need to be given to you. Here's one. Carbon plus 2 hydrogen yields CH4, and the delta H for that is negative 74.8 kilojoules per mole of methane. That in of itself isn't important, but these are possible steps. You'll see how they come together. Here's another one. Carbon plus oxygen yields carbon dioxide. And this one is also exothermic, giving off negative 393.5, well, a little crazy on the periods, kilojoules per mole of carbon dioxide. And then here's another step. Hydrogen plus a half an oxygen. What? Who leaves it like that? Had to look it up in a book. This is what they gave me. Gives me this. So these are things I'm giving you. These are 3 kind of separate reactions. But what we're going to do with these is we're going to try to manipulate them to have them be like, in this reaction, first this happens, then this happens, then that happens. Each one of these you can see is exothermic. So here's what we're going to do. We're going to manipulate so they add to the equation we want, which is this one. That's our goal. And I'm going to show you how to do that. And you're going to have some of these in your questions and problems to try. So here's what we're going to do. I'm going to look at this very first one. Carbon plus 2H2 yields CH4. When I look at this, first of all, there's no carbon or hydrogen by itself in this original equation right here. But there is a methane. Here, that's CH4, that's methane. Here methane is being produced, but in this reaction we want it to add up to, it's being used up. So what I'm going to do is I'm going to take this first reaction and I'm going to reverse it. I want the things to be on the proper side of the arrow. Here it's on the right side of the arrow. I need it on the left. So I'm going to reverse number 1 and I'm going to write it backwards. So CH4 gives me carbon and 2 hydrogen. Well, here's the thing. If it was exothermic this way, what do you suppose happens if I'm doing the reverse reaction? It's endothermic. So my delta H becomes positive 74.8 kilojoules per mole of methane. How many moles of methane do I want in my original equation? 1. So I only need 1 of these, and so I'm actually going to multiply this by that 1 mole of methane that I need. All right, so that's the first one. Now let's take a look at the second step here. Again, I don't have any carbon. I do have oxygen, and I would like that on the left side. And I do have carbon dioxide, and I would like that on the right side. So do I need to flip this one over? No. No. Now, I take a look. How many carbon dioxides do I need in this equation? 1, and I have 1 here. I need 2 oxygens, but I only have 1 here. But is there anywhere else that I'm going to get oxygen from? The next one. So I'm not going to worry about that. I'm going to look at my carbon dioxide. So I'm going to leave this one alone. Carbon plus oxygen yields CO2. And since I didn't flip it over, I'm not flipping my sign. I'm just leaving it alone. And I only need 1 mole of CO2. So I'm basically getting these to cancel out. So I can just get joules or kilojoules. All right, let's look at the third one. Do you suppose I need to flip the third one over or not?
No.
Why not?
H2O is on the right.
Water's on the correct side, and so is the oxygen, actually, right? So I don't do that. I'm just going to write it as is. Do I have the right numbers of oxygen? Well, let's say of water. We'll start there. Do I have the right number of water? No, because I need 2, but I only have 1 here. So I'm going to just multiply this by 2, right? I'll make this a 2, this a 1, and this a 2. I just doubled the whole equation, which is how we prefer to look at it anyway, get rid of that fraction. All right, so my delta H, I didn't flip it over, so I am not changing the sign. But I multiplied everything by 2, so I've got to account for that here. Now here's what I want you to see. If I take these 3 equations and I add them together like a math problem, I'm going to see if they add up to the equation I want. And here's how you do it. Anything that's found on the left side of one arrow and on the right side of the other arrow, I can cancel out. If things are found on the same side of the arrow, like these guys, both on the left side, I have to add them. So is there anything that you see that would cancel out? Brett? Carbon, right? Here's carbon on the right side of this arrow, but on the left side of that one. What else? Mike? Hydrogen. So here's 2 hydrogens on the right side of this arrow and 2 hydrogens on the left side of that arrow. So they cancel out. Anything else? No, because the oxygens won't cancel because they're on the same side of that arrow. So I can start dropping everything down. Anything on the left side of those arrows, I just drop down to the left side of this arrow. It doesn't matter what order. So CH4 plus 1 oxygen plus another oxygen gives me 2 oxygen. And on the other side of the arrow, carbon dioxide and 2 water. Is everyone with me how I did that? Armin, question?
You can't say in the same equation there is a C in the reactant standard product for you that
If there was, you could, but you won't see that because we won't ever have this inside the same equation having something on both sides. If there was for some odd reason, yeah, you absolutely could cancel it. Now, if I was able to add up my equations, then Hess's law says it doesn't matter. Now, this is literally like different steps happened. Like, hey, first the methane broke down into its elements. Then one of the elements bumps into an oxygen and forms a carbon dioxide. Then the hydrogen bumps into another oxygen and forms water. It's almost like, hey, this happens, and then this happens, and then this happens. These are the steps. So Hess's law says it doesn't matter how you get there. So if you can add up those equations, you can also add up those energies. So 74.8, notice this stuff cancels. So what will my units be when I add this all up? Just kilojoules. So 74.8 plus a negative 393.5 plus a negative 285.8. I have that number somewhere. Negative 890.5 kilojoules.
So you times it to 85.
I apologize. Yes, you take negative 285.8 times 2 for that. Otherwise, you won't get this number. Does that make sense? Now we have to interpret this. A wine. It's not good for you. All right, so let's interpret. Here's the stuff we need to know about this. Remember, this is all about a way of getting delta H for the reaction on paper. This could be written a couple different ways. Ryan, question? You take, go ahead and pull your calculator out. 74.8 plus a negative 3, now I didn't do the times 1, plus a negative 393.5 plus a negative 285.8 times 2. That was the part I forgot to say originally. Then you get this. Because these are multiplied by 1, so you don't have to enter those in your calculator. All right, here are some ways to interpret it. You could write this, first of all, is this reaction endothermic or exothermic based on this delta H? Exothermic, of course it is. It's, you know, burning methane. So we could write this CH4 plus 2O2 yields CO2 plus 2H2O and say delta H is negative 890.3 kilojoules. And we could just leave this as one interpretation. A delta H that is attached to the equation. But we like our delta H's as kilojoules per mole or kilojoules per gram. So here's how we do that. If we want to do that, we could say delta H for the reaction is negative 890.3 kilojoules per, and now we pick something in the balanced equation that we would like it per mole of. So maybe I want to know how much energy do I get per mole of methane burned? Well, according to my balanced equation, there's 1 mole of methane in it. So I could say it's negative 890.3 kilojoules per 1 mole of methane. That would be an okay interpretation. Or I could say delta H for the reaction is negative 890.3 kilojoules per, say, 2 moles of water formed. Where did I get the 2 from? Balanced equation. Oh, but I wouldn't leave that like that. So negative 890.3, that's negative 445.15. So negative 445.2 kilojoules per mole of water. Ryan? They're related because they both come from the balanced equation in that way. Yeah. Mike?
So it doesn't matter, we can use like either one of those or any other thing.
Yeah, I mean, what if I had a problem and I said, hey, you know, 4 moles of oxygen was used up. How much energy could I get out of it? Then I might say, oh, well, I know my delta H reaction is negative 890.3 kilojoules per how many moles of oxygen? 2.
Don't you? Okay.
So if I had said 4 moles of oxygen is used up in this reaction, how much energy could I get out of it? This could be my conversion to help me go from moles of oxygen to kilojoules, right? So if my problem was you're using up 4 moles of oxygen, 4 moles times this many kilojoules over 2 moles, I could find out how much energy. So you can interpret this number per any one of these moles in the balanced equation. Pick which one's most helpful in that case. Okay? So if I had a problem, just as an example, and the question was how much energy is given off by the combustion of 127 grams of methane, And I already knew that delta H for the reaction was negative 890.3 kilojoules per 1 mole of methane, because that came from the balanced equation. Well, then I can take my 127 grams of methane, convert it into moles, and then I can use this as my conversion, because I get negative 890.3 kilojoules per mole of methane. And I get negative 7,070 kilojoules. That's how much energy I would get if I burned 127 grams of methane. So that's one way to interpret it. The only way you can do all this work, though, is if you're given those steps. The ones where I said possible steps. That only works if I give you the possible steps. Some of these questions and problems, like, I know 48, it might be a couple of them, they give you some steps. And they say what reaction you need to get to, and you have to flip them around or multiply them to try to get to that number.
So, like, when we say, like, it's negative 890 kilojoules per mole of CH4, could you turn that into grams of CH4?
You could if you wanted to. If you would prefer it to be in kilojoules per gram, like we did the candle. I mean, honestly, you could just do a step here and go, oh, in 1 mole of CH4, it's 16 grams. That would cancel and get a new number. It would be a different number for kilojoules per gram, but absolutely you could do that. Yep. Or if we wanted to take our candle that we did in kilojoules per gram and convert it into kilojoules per mole, we could do something very similar there too. All right, there's one other thing, though, because that's a really long way, and sometimes you don't want to do it the long way, and sometimes you don't have to. So what I want you to do is I want you to find your worksheet, the one we've been working on, and I want you to look at the chart on the back side of it. So find that worksheet. There's a chart on the back side. It's not working. Okay. Is everyone fine on the chart? There's a big chart. It says heats of formation on it. Do you see?
Enthalpy.
Oh, I'm sorry. Enthalpies of formation. I don't have mine in front of me right this second. That chart I'm going to have you look at in order to consider Hess's Law short. This is the short version. And if you are not given equations that you have to mathematically manipulate, you can do it the short way, which is, as the name suggests, much shorter. All right, here is what Hess's Law short does. It's where you mathematically use heats of formation, or enthalpies of formation, as that chart says, which are called delta H sub F. So now we have heats of fusion, we have heats of vaporization, we have heats of reaction, and now we have heat of formation. They're all just amount of energy per joule or per mole or per gram. Anyway, we mathematically use heats of formation, delta H sub F, in order to find the delta H of reaction. Now I have to tell you what that enthalpy of formation means. So delta H sub F, which as that table tells you is the enthalpy of formation, by definition is the amount of energy required to make 1 mole of a compound from its elements. The amount of energy required to make 1 mole of a compound from its elements. I'll give you some examples. All right, so here's what I want you to find on that table. See if you can find C2H6. Can you find C2H6?
Yeah.
What is the number for that?
-84.7.
Negative 84.7. What are the units on that table? Should say at the top, I think. Kilojoules per mole. What that means is, because this is the amount of energy to make 1 mole of a compound. So if I were to make 1 mole of C2H6 from its elements, well, what elements are making that up? Carbon and hydrogen. So I would need 2 carbons and 3 hydrogens. I just balanced it, right? Those are the elements that make it up. Then delta H for that reaction would be negative 84.7 kilojoules. In other words, it would be an exothermic reaction, and I would get that many kilojoules per 1 mole of C2H6. So basically, that table is like a list of stuff that scientists came up with. Like they did experiments for each one of those, and they created that compound, and they found out if it gave off energy or if it took in energy. Are more of those numbers endothermic or exothermic? Exothermic. So a lot of them gave off energy, and they measured it. And that's where that table came from. So we can use that. So this is just an explanation of what that means. Now, notice that every single thing on that table is a compound. There are no elements. Can you find hydrogen, H2? Where? Okay. Look for oxygen, O2. Or carbon, or sulfur, or tungsten, or radon, or sulfur, or phosphorus. There are no elements on that chart by itself. Because the delta H for formation of an element is defined to be 0. Like there is no energy for the heat of formation of an element. So they don't put the elements on the table. Now you'll get a table like this on your test, or at least some variation thereof. And almost certainly someone will come up to me in the middle of the test and say, Mrs. May, I can't find O2 on this table. And I'll stare at you and say, go sit down. And you'll be like, gosh, she's so mean. There's no elements on that table. Okay, so you're not going to find them there. Because the heat of formation is defined to be the amount of energy to make 1 mole of a compound. They don't fit that category. I mean, how do you make phosphorus? It's an atom. I mean, you'd have to literally put the protons and the electrons and the neutrons together to make it. So there's no bonds that have to form inside of that. Mike? You won't. But I would give you any specific heat capacities you need or anything like that. I mean, you need to know water. I've said that. Liquid water. But anything else I'd give you. Okay? All right, now, I haven't actually got to the short method. This is sort of just background information about what this table is. Here's the short method. Whoops. The delta H, this is the formula for it. Delta H for the reaction is equal to, this is a mathematical operator. Anyone know what that means? Summation. It's like an epsilon, capital E in Greek. It means summation. So the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. This is Hess's Law short, which might not mean anything yet, so I'm going to do the example with you, the same one we just did, so we can see how it works. So here is my reaction that we've been working with. Now I'm going to add some states of matter because it's going to be important because water exists as a couple different things. Typically in a combustion reaction, the water produced is liquid. I know it sounds a little odd, but they've actually shown that via experiment that that's what happens. Now, in order to do this, we have to remember who the products and the reactants are, because if you get those mixed up, you get this wrong. So, CH4 and O2, are those reactants or products? Reactants. And these guys, of course, are the products, and that's just important to know. So here's how Hess's Law works. Delta H for the reaction is equal to the sum of the heats of formation of the products, so that's these guys. Now, I do have to incorporate from the balanced equation how many moles are considered. So here's what I will do. I have 1 mole of carbon dioxide, and I need you to look on that table and find carbon dioxide. Negative 393.5. Now remember, the units from that table are kilojoules per mole, right? So you can see that my moles will cancel. So this is for the carbon dioxide. That's what I'm doing right now. Now go ahead. But I have to add together the other products, and I have 2 moles of water. Can you find the heat of formation of water as a liquid? Negative 285.8. Is everyone else finding that? Is that the right number? Okay. All right, so I did this. So what I've done is this whole thing, this is the sum of the heats of formation of the products. Then I need to subtract. Minus the sum of the heats of formation of the reactants. So now I do the same thing. All right. I've got 1 methane. So 1 mole of methane. What is it? Negative 70. Okay. Negative 74.8 kilojoules per mole. Plus, oh look, 2 moles of oxygen. What's the heat of formation of oxygen? 0. Now this is fun with not losing your negative. Pull out your calculator, throw that in. Let's see if you can get an answer and not lose track of your negatives. That's the hardest part, is just making sure you enter it right. You don't lose a negative sign, something like that. Anyone get one yet? An answer? Negative 890.3. Does that sound familiar? That's the right answer. Did you get it? Hey, but look, if I scroll back to this other one, hey, remember back here? We did it the long way, given some steps and some energies, and we found this. Or, if we use the heats of formation, oh look, we find the same number, which then, because that number is attached to this equation, so then I can do all those interpretations. Oh, delta H reaction is negative 890.3 kilojoules per 1 mole of methane, or per 2 moles of oxygen, or per 1 mole of carbon dioxide. That kind of thing. Still felt long? It just depends. How you do the problem, it's not so much a choice of, gosh, I would really like to do it long way or short way. What it is if you are given a bunch of steps in the reaction, you'll do it this way, because that's the information you have.
So you'd be given those steps?
You'd be given those steps.
All right.
If you're given steps, and like I said, some of these questions and problems, I know 48 for sure, and maybe 46 too. They give you steps, and they give you energies, and you just have to manipulate them and get practice doing that. So if they give you steps, you can do it that way. If you aren't given steps, then write a balanced equation. These all, of course, need a balanced equation. And then do heats of formation of the products minus heats of formation of the reactants.
So if you were given those steps,
You'd be given the delta H's for each step. Is that what you're asking?
Yeah.
Yes, you would. All of this, you guys, goes back to this original problem. Remember when I gave you this problem and I said, hey, well, you know, we have this problem and you get this delta H of reaction, but we got this delta H of the reaction in the lab? Doing either the long way or the short way is simply another way to find delta H for the reaction so that you can use it in a problem. But you have to write a balanced equation and then either manipulate steps that are given to you or use the chart to figure out what that is. And that's how you have a piece of that information. As you start working on some of the problems on that thermodynamics worksheet, there will be some problems that say, not this problem, but methane is burned in oxygen. Figure out how much water it can heat up at, and then it gives you more information. Well, the only way to do that is you have to write a balanced equation for the methane, figure out what the heat of reaction is for the methane plus oxygen yielding carbon dioxide and water, because then you can figure out how much energy the methane gives off. So think about that as you start working through problems. Armin? Because everything we talked about today is a way to find this number on paper. No, because this was about a candle. But if instead this said, hey, if 2.95 grams of methane are burned and used to heat 100 grams of water, but we didn't go in the lab and get this number, you could get this number now. Because you could write a balanced equation for methane and look at that chart and do products minus reactants and find this number. So it's a way to get that on paper.